Hello everyone, here I wanted to go over 4 main examples on integrating factors for exact equations. Now what that really means is that these equations look exact, the ones we'll see in these examples, look like they're exact type of equations. You have something times dx plus something times dy equals 0, but they're not exact as it turns out. If you take the derivative of this with respect to y and the derivative of this with respect to x, you won't get the same expression. But there's kind of a way to make it exact, and what I mean by that is you can multiply through by some integrating factor that will actually make this an exact equation. But right now, as is, it's not. And you can check that if you want. Take the derivative of this with respect to y, take the derivative of this with respect to x, and you'll see you won't get the same expression. Now, what I'm going to do is I'm going to call that integrating factor r, and r is going to be a function, but I'm going to multiply through by r. So in doing that, I'm going to do it kind of simply. We'll get r times this guy, dx, plus r times this guy, dy, is equal to r times 0, which is of course 0. Now, in general, r can be a function of x and y, but the problems I'm going to go over today hopefully will only be in terms of x or y. If you can't get either of those to work out for some reason, there are special cases of functions in terms of x and y, but to do it in general is very, very, very messy. So we're going to hope and cross our fingers that it's only in terms of x or only in terms of y. It makes the calculation a lot easier to handle. So right now, let's just imagine r is equal to some function r of y. Now it could be r of x or it could be r of y. Now I know it'll be a function of y only because I've done this already just to make sure it worked out. Now if you were to, by the way, this should be a y, sorry about that. If you were to let it be a function of x and run through the same argument I'm going to, you'll get to some point where something won't happen. So I'll mention that when it happens here, but it won't happen if it was a function of x. And that's how you know something is wrong. So let me kind of explain. So derivative of this, so this is now our new m. So let me kind of write that in red here. So remember, for exact equations, you have m dx plus n dy, where m and n are functions of x and y. Okay. So now if we take derivative of m with respect to y, since r is a function of y, we need product rule here. So we're going to get r prime times the regular of the other expression, y squared plus 3xy cubed, plus r times derivative of that expression, which is 2y plus 9xy to the second. And again, this is just by product rule, because since r is a function of y, r prime is derivative with respect to y. Okay, good. This is supposedly equal to, according to the check, remember that's that my is equal to nx in order for it to be an exact equation. We're going to take derivative of this with respect to x. Now the nice thing here, since r is a function of y, it's a constant in the eyes of x. So this is really just going to be r times the derivative of 1 minus xy. Well, derivative of 1 is 0. Derivative of xy in terms of x is just going to be y because you drop the x. Remember that derivative of x is 1, so derivative of x times y is 1 times y, in which case this is actually negative y. Okay, so we want this equality to work out. So let's see what r has to be if this is true. Now in this case, what we end up getting is kind of a separable equation, basically. We can move all r's on one side, keep this r prime, and then we'll separate things at the very end, keeping in mind that r prime is the same as dr over dy in this case, of course, because r is a function of y. Okay. So let's see. So I'm going to subtract this to that side. Yeah, that's fine. I'm going to write this in a little bit of detail, but it's not going to be too hard to see, hopefully. If you subtract this to that side and pull out r from everything, you get negative y here, minus 2y minus 9x y squared. So I hope that's okay. Subtracting this thing to that side and distributing the negative gives you those two, but since you have r times this one, which is on that side, and r times this, pulling out r from each of them just gives you this, actually. Now, of course, here, these actually combine to negative 3y. So just to kind of save some space, let me do that over here. And then finally, dividing by this gives us something kind of interesting. Okay. So of course we get cancellation. And what our real goal is to do is to try to separate things. But really what we want is, since I'm going to separate to get r prime over r on this side, remember that r prime over r is 1 over r times dr over dy. So if we multiply dy to the other side, then you'll get this is equal to something times dy. And we'll do that eventually. But before we get to that point, just kind of realize, once we get to this point, this integrand here better be only in terms of y. Because even though we're treating x as a constant, when you take partial derivatives and all that, that's fine. But in terms of separable equations, x is a variable that y depends on. So in that context, it doesn't make sense to have x's and y's. In fact, it wouldn't make any sense because that would mean that r would not be only in terms of y, it would be in terms of x and y. And we're assuming that it's only in terms of y. So with that being said, hopefully the x's here somehow cancel out. And that's what won't happen if r is a function of x. In terms of y, it ends up working out. Now let me show you. I'm going to factor the top of it. So we factor the top, I'm going to pull out negative 3y. So they both have in common anyways. We get 1 plus 3xy. The r I already took care of by dividing to this side, so that part's fine. And now here, on the bottom, if we pull out a y squared, look at that. What do we get? We get 1 plus 3xy. It's pretty magical. These actually end up canceling out. If you let r be a function of x, you'll get something weird where the signs aren't even the same, where it's like 1 minus something over 1 plus something. There's no real way to make those cancel out like it happened here. So if you get to a point where it doesn't seem to make sense no matter how hard you try to factor top and bottom, there's no cancellation of one of the variables, so that r is only in terms of what you want it to be in terms of, then try the other one. And if that doesn't work, then you can possibly try some special cases. But let's continue. So of course this reduces to negative 3 over y. And in fact, from here, if you want to integrate both sides to completely solve for r, we end up getting that ln of r, it's absolute value of r, but we really only want a particular integrating factor. We don't need a general integrating factor. So I'm just going to say it's ln of r, so I'm assuming r is a positive value basically. And antiderivative of negative 3 times 1 over y is negative 3 times ln of y. And then we know what to do from here. Hopefully you can take both sides as powers of e. And again, I'm not writing plus c because we're just looking at a particular integrating factor, not a general one. So we don't actually need that. Here these cancel out, here not so much. Well, they kind of cancel out, but not quite. One way of doing this is to bring negative 3 inside the ln. And in doing that like this, then the e and ln's cancel, and you get y to the negative 3, which is 1 over y cubed. Fantastic. So we're going to roll with that. R is equal to 1 over y cubed. And now what we're going to do is I'm going to erase everything here up to this point, plug in 1 over y cubed for r, and then we'll actually see what the solution is based on that. All right, here we go. I've erased everything up to the original question, basically. We found out that an integrating factor should be 1 over y cubed in order to make this exact. Multiply through by y cubed. Y squared over y cubed is 1 over y. This is going to be, well, I guess just 3x. Okay, that's 1 over y cubed. Y over y cubed is y squared, so it's going to be minus x over y squared. Y squared in the denominator is what I meant to say. Continue bordering that off. Very good. So now derivative of this with respect to y is going to be negative 1 over y squared plus 0, because that goes away. Derivative of this with respect to x, that goes away because this is in terms of, well, y only. Derivative of this with respect to x, drop the x, and you get negative 1 over y squared also. So that's a quick check to see that this is indeed exact. So now we'll follow through the steps to actually find a solution to this exact equation. And remember, the way we do that is we take a look at, let's say, this guy, which is the derivative, partial derivative with respect to x. And then we're going to take the antiderivative with respect to x, of course. Antiderivative of 1 over y with respect to x is 1 over y times x. Antiderivative of the other term is 3 over 2x squared. Okay? And now we're going to take the derivative of this with respect to y and match it with this guy. Let me just make sure on that. Oh, right. So when you take the antiderivative with respect to x, you get plus a constant, of course. Now it's very possible that constant could be a function of purely y. Let's call it g of y. And that's of course is because the derivative of g prime of, well, of g of y, I guess I should say, with respect to x would be 0 because it's a constant in the i's of x. So now, taking derivative of this with respect to y gives us well, this is negative 1 over y squared times the constant x. And by the way I'm getting this is that 1 over y, if you don't know, is y to the negative 1. Its derivative is then negative 1 times y to the negative 2 by power rule. And that's, of course, equal to negative 1 over y squared. So I probably should have mentioned that earlier, but that's how I'm getting that for the derivative of 1 over y. Okay? Derivative of this with respect to y is 0. Derivative of that with respect to y is g prime of y. And now if we compare these, so we want this to be equal to our n function, 1 over y cubed minus x over y squared. What you'll notice is that these two are exactly the same. So we can just add that to both sides and cancel these out. Add x over y squared, that is, to both sides. So we've discovered that g prime of y must be y to the negative 3. So by taking the antiderivative with respect to y, we get g of y is equal to add 1 to this power to get negative 2 and divide by negative 2 to get this. Of course, you can also write it like this, let's say. But anyways, that's g of y. So now we know exactly what our function is. And that's basically it. So our function now is going to be, let me write it like this, x over y plus 3x squared over 2 plus g of y, which is actually negative, so let me write minus 1 over 2y squared equals some constant. So that's the thing, that when you find the actual solution to an exact equation, you find the function of two variables whose derivative with respect to x is m, whose derivative with respect to y is that, and the solution to the exact equation is that function equals some constant c. So that was kind of a long problem, but like I said, we're going to do 4 of them. This is the first one. So now let's take a look at the second example right now. Right, so this next problem is actually very, 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 very tricky. This one kind of has been throwing me off for quite a while. The solution I found out just by trying a bunch of different things, and it's a little disappointing, I think, because you want to try to do it based on the techniques I've been trying, but it doesn't actually work out. If you let your integrating factor r be in terms of purely y or purely x, it doesn't work. If you try a special case, and I mentioned there are special cases where r is in terms of x and y, and one would be a power of x times a power of y. Try to use something like that, figure out what m and n are by using our check, derivative of this with respect to y equals derivative of this with respect to x. That unfortunately doesn't work out either. So what can we possibly do? Well, the first thing I notice is that if we multiply through by x, that's not quite an integrating factor, I don't think, because it doesn't really work out, but we get something that is still not an exact equation, but we can work with this, and it's easier to work with because we don't have to deal with the quotient rule when taking derivative of things like y over x. And it looks more symmetric. There's more symmetry going on here. Now again, if you try to find your integrating factor based on this differential equation, it looks a little easier, the math is easier, the calculus of finding derivatives is easier. But it's still not quite there, and what really throws things off is the e to the xy. So, I decided, why don't we just divide through by that? I mean, when I took derivatives of each side with respect, or of each of these with respect to y and with respect to x, what happens is you can't get away from the e to the xy. So something times e to the xy, and by product rule basically, something times e to the xy. In other words, you'll have, when you take the derivative of this with respect to y, you get some factor times e to the xy. Similarly here, derivative of this with respect to x, you get some factor times e to the xy. And then that equation just divided by e to the xy anyways because it's non-zero. So I kept wondering, well, what if we just did it ahead of time? And then, well, actually something kind of magical happens. If you just divide it by that ahead of time, you end up getting this. Which in fact, this is exact. Why is this exact? It's exact because the derivative of this with respect to y is equal to 0. Derivative of y with respect to x is also 0, and these are the same. So there we go. So in other words, what do? We multiply through by x, then we multiply through by e to the negative xy, and that get rid of e to the xy. Because multiplying by e to the negative xy is the same thing as dividing through by e to the xy. And that actually makes it exact. And again, it's a little bit weird and tricky. It's an integrating factor that involves x and y, but it's not of a particular special form. It's just looking at this and thinking, we're trying the best we can. What can we get rid of to make it look more simple? And you get rid of the fractions by multiplying by x, and then after a little bit of tinkering, get rid of the e to the xy's by dividing through by that, and you end up with this integrating factor, and this works. So now, when we multiply through by this, we just get this guy, and this is actually really easy to solve. It's just separable. So in fact, if you just separate things by subtracting this to that side, and dividing through by, well actually we wouldn't even need to divide through at all, do we? We can just take the antiderivative. We get y squared over 2 is equal to negative x squared over 2 plus a constant. And then that's a good implicit solution, so we can stop there. Or if you want to take the, do it the way I showed you, take antiderivative of this with respect to x plus some function in terms of y, and then take derivative with respect to y. That goes to 0, you get g prime of y. And then you can take, you can compare this to y, in which case that implies g is the antiderivative of y, which is, well, y squared over 2. So you end up getting that x squared over 2 plus y squared over 2 is equal to some constant. And it's exactly this, notice. And in fact, it's kind of interesting, but this particular differential equation, although it looks messy and it's hard to solve via integrating factors for exact equations, it's actually a separable equation in its own right. If you move things around, the e to the xy's cancel out anyways. That's what made this problem look a little more difficult, or made it look more difficult than it actually was. Okay, so that was nice. Now on to the next example. Right, so for this one, the first thing I want to do actually is look at this, I guess, function, what we call usually m. And if you split this up, you can write this as y to the negative 2 e to the x, plus y to the third over y to the second is just y, that's times dx, and then plus 3x dy. So now we want to find an integrating factor r that is, well, either purely in terms of x or purely in terms of y. If it is in terms of x, then this will require a product rule, and I don't like that. Because if r is in terms of x, then multiplying through by r will give you something like this. We write it as 3xr dy. Derivative of this with respect to x will be, well, derivative of 3x is 3 times r plus 3x times derivative of r. That's just product rule. But this is purely in terms of, of x. This will be purely in terms of y, because the derivative of this with respect to y will be whatever this is. Since r is in terms of x, it will be a constant. And we'll have a contradiction because you'll have, well, a thing only in x equals something only in terms of y. Well, not only in terms of y, but you'll have a y there. So it contradicts the fact that r is only in terms of x. So let's actually let r be a function of y. I think that'll make a little more sense. And let's see what happens. So in this case, what happens is we actually don't get a product rule happening here. Since r is a function of y, it's a constant in the eyes of x, so its derivative here is just 3r. Derivative of this with respect to y now, well, here we'll need product rule. And this will be r prime times regular of this, y to the negative 2e to the x, plus y, plus r times derivative of this, which is going to be negative 2y to the negative 3 e to the x. Let me kind of rearrange this a little bit, plus 1. And that's equal to, again, derivative of this with respect to x was just 3r. So I hope we see where I'm getting this from, but again, this is just product rule with respect to y. And this is separable. If you move all the r's to one side and combine, well, distributing this, notice you get this times r plus 1 times r. But when you subtract that, 3r minus r is just 2r. And pulling out the r just gives us essentially 2 minus that 2y cubed e to the x term. In fact, it's plus because we're subtracting it to the other side, so the sign changes. I'm kind of skipping a little bit of steps here, but hopefully you can kind of follow. Subtracting this makes it positive. Subtracting the 1 from this 3 makes it 2, because we're pulling out r anyways. Here, we end up getting this. And we want to cross multiply and cross divide to get r prime over r, basically as we kind of saw the previous types of problems, because of course this is a separable equation now. So we're getting r prime over r, equals dividing by this to the other side. And in fact, I'll factor this at this point in time. Really, all I can factor out is just a 2. Okay. And we get 1 plus y to the negative 3 e to the x. And here I want to, so I'm going to divide this, I'm going to write this here, down here. But if you rearrange the terms, you have it like this. And it looks pretty suspiciously similar. We have the plus in between these two terms, we have e to the x on one of them. In fact, if we were to make this 1 by factoring out a y, this would have to be negative 3. Let me see if that makes sense. Yeah, I forgot a negative 2 here. There we go. Now that works, because distributing this y back in, you get y, and then y to the negative 3 times y is just y to the negative 2, so you end up getting that back. And this is nice because this allows us to cancel that x. Why we wanted to cancel out the term involving x is again because we want r, I guess, to be a function purely in y. So what we end up getting now is that, well, this, which remember is just 1 over r dr, because r prime is dr over dx, or I guess in this case, dr over dy, multiplied by y to the other side, by dy to the other side, we get this. And at this point, you can just kind of see that r has to be y over 2. That definitely works out. Actually, does it work out? Let me see. No, it actually doesn't work. I mean, it looks kind of like it works out, but that's not quite the case. You have to be a little more careful than that. So we do actually have to take the antiderivative. But at least you kind of see that that's a possibility for someone to possibly make a mistake, maybe. I don't know. So the derivative, the antiderivative of this is ln of r. Antiderivative of that is 2 ln of y. You bring the 2 in as a power, you get this. And now we find out by taking both sides as powers of e that r must be equal to y squared. Now again, in this case, I'm kind of just avoiding the whole plus c scenario because it's just an integrating factor. So we find out that r has to be of the form y squared. So we're going to roll with that, and then I'm going to erase things, and we're going to actually try it out and find out what the solution to this differential equation is. Okay, so now multiplying through by y squared, we'll cancel this out actually and just give us e to the x plus y to the third dx plus 3x y squared dy. And notice, quick check. Derivative of this with respect to y, that goes to 0, that becomes 3y squared. Derivative of this with respect to x, drop the x, you also get 3y squared. So it's a quick check to see that this is indeed exact now, using that integrating factor we just found. So now take the antiderivative of this with respect to x, and we get, well, e to the x plus y cubed x plus some function g of y. Take derivative of this now with respect to y, that drops, that becomes 3y squared times x plus g prime of y. And if we compare this to our end function, 3xy squared, we see that these two have to be the same, so that implies that g prime of y is equal to 0, which implies that g of y is some constant, but we'll just call it 0 itself. And the reason again why we do that is because remember that for the function of two variables x and y, let me just put that over there, that's always going to be equal to a constant, so it won't really make a difference. So let me kind of show that actually. So this is our solution with g of y being 0. So what I really mean by that is our solution to this differential equation is this function of x and y, e to the x plus y cubed x equals some constant. Now, if instead of calling this 0, if we called it a constant itself, we'd have this plus a constant, subtract that other constant to this side, constant minus a constant is a new constant. So for exact equations, you don't really care about constants until, or adding constants I should say, until the very, very end where you write your function of x and y equals some constant. Now, in the last problem I left it implicit, I meant to say, and we could have actually solved for y explicitly there. You would have gotten a radical involved. Here we could do the same thing, subtract e to the x divided by x, and then take the cube root. And that would be fine, but again, I'm going to leave it implicit just because I'm being a little lazy about it and I want to move on. So now finally, let's take a look at the last example now. Right, so I've been trying this problem for a little bit of time too. These ones are kind of tricky. This is actually very, very similar to the second problem we saw today. Now, to kind of to make it look simpler by getting rid of the denominator, what we can do is multiply through by y. But in multiplying through by y, we might as well divide by 2. So let's actually multiply by 1/2 y. And the motivation for this is because here, this is a multiple of 4, but this is a multiple of 2. These both have 2 in common. So just divide by 2 basically is what I'm saying. So we get 2 times y squared plus x. And here we just get x plus y squared. Because we're dividing by the 2's and multiplying by y, so the y cancels. But in fact, here I forgot to write this y. And I also forgot to write this dx and this dy, of course. So now from here, we can try to find a integrating factor r such that, it's either in terms of x or in terms of y. In this case, so purely in x or purely in y. But neither of those will work out. You'll actually get contradictions for both of those. So you may need to go back and think of that second problem we saw today. What can you do to make it look even simpler? Well, it looks a little tricky the way it's written, even after simplifying a bit. But after looking at this quite a bit, you'll realize these are the same. So why not just divide through, and I forgot to write equals 0 here from the original equation, but might as well just divide through by that. So if we divide through by 1 over x plus y squared, what do we get now? We get 2y dx plus dy equals 0. And this is indeed exact because derivative of this with respect to y is going to be 2. And derivative of 1 with respect to x is actually 0. So that actually doesn't quite work, actually. It was close. But I guess at this point, it's not too hard to find out what an integrating factor is. But I think here, dividing by this common thing, that definitely helps a bit. So instead of finding an integrating factor there, let's just do that here. So really what we did was we multiplied through by y over 2 times the quantity x plus y squared, and that gave us this. So let me kind of clean this up a bit here. And then from there we can try to find the integrating factor. So multiplying through by this thing, we end up getting a simpler looking exact type of equation, which again is just going to be 2y dx plus 1 dy. Now again, it's not quite exact as this. Derivative of this with respect to y is 2, derivative of this with respect to x is 0. But maybe some integrating factor in terms of purely x or purely y works. If it's purely in terms of y, I don't think that's going to cut it because its derivative here will still be 0 and this derivative will be non-zero. So I'm going to say it's a function of both x, or just x, for its sake, just x. So let's do that. Let's multiply through by this times r. So it's going to be 2yr and then r dy, something like that. Now derivative of this with respect to y is going to be, we'll drop the y, you just get 2r. Derivative of this with respect to x is just going to be, well, r prime. So there we go, we get 2r is equal to r prime, that's separable. So that gives us a 2 is equal to r prime over r. We've seen this quite a bit, we know what this means. This means that, well, 2 dx is equal to 1 over r dr. The integral of 1 over r dr is ln of r. The integral of 2 with respect to x is 2x. So that means that r is equal to e to the 2x. So in fact here, our actual integrating factor is r is equal to y times e to the 2x, y times e to the 2x, all over 2 times the quantity x plus y squared. Wow. So now I'm going to erase everything. We'll try this integrating factor and let's see if it works. All right, so we did a lot of brainstorming to see that this is hopefully the correct integrating factor. So let's see, multiplying by this integrating factor here will give us, well, 4 over 2 is just 2. We gain a y, we gain e to the 2x, and the y squared over x, y squared plus x part goes away. So we get this times dx plus, over 2 cancels those 2's, the dx plus a y squared is canceled as well, the y is canceled, and we just get e to the 2x dy. And now we can check derivative of this with respect to y, drop the y, we get 2e to the 2x. And look at that, derivative of e to the 2x with respect to x is indeed 2e to the 2x by a chain rule. So now we can take the antiderivative of this with respect to x, and we just get, well, y to the 2x. Basically, you have to divide by 2 because the derivative of e to the 2x is, well, 2e to the 2x. It's kind of like a U substitution thing. It's basically the anti-chain rule, essentially. Antiderivative e to the 2x is itself, but instead of multiplying by 2, you have to divide by 2, so the 2 is gone. Then, take the derivative of this with respect to y, the y gets dropped. By the way, I forgot to write plus a constant, which is possibly a function of y, so we call it g of y. Now we can take derivative with respect to y, the y drops for the first term, plus g prime of y, and then we compare this to our n function, which is just e to the 2x, implying that g prime of y is equal to 0, implying that g of y is just a constant itself, but we'll actually just call it 0 for the purposes, for our purposes anyways, as far as exact equations go and the way we solve those. So with that being said, this guy here, because g of y is going to be 0, we're going to take it to be 0. This equals c is going to be our implicit solution to this differential equation. And the last two we could have solved explicitly. Here we could solve explicitly, and I'll just do it real quick. Solving explicitly gives you y is equal to c e to the negative 2x, and of course that's because dividing each side by e to the 2x is the same as multiplying by e to the negative 2x. And these are both okay, so I could box both, but I'm going to box this one. I think it looks a little nicer. And of course, if we had a initial condition, we can go ahead and apply that to solve for c, but we don't. So I'm going to end that here, and I'm going to end the video. And again, here we're just doing some examples, 4 problems in particular, of integrating factors for exact equations. Hope you enjoyed. See you in the next few videos. Thanks for watching, and like always, I'll see you then.